Linear Algebra II, Lecture 14, Symmetric Operators. Let us start with a quick recap of what we did during the previous lecture. Let V be a vector space and F a linear operator on V. An eigenvector for F in V is a vector V such that f of V is equal to lambda times V for some real number lambda. A real number lambda is called an eigenvalue for F if there is a non-zero eigenvector for this lambda. And the eigenvalues for F are exactly the roots of the characteristic polynomial of F, which is defined as a determinant of the following matrix. We choose any basis bold V in V, we take the matrix of F in this basis bold V, and we subtract x times the identity matrix. So we get a square matrix and we take the determinant. This determinant is a polynomial in X of degree the dimension of our space. And the eigenvalues are exactly the roots of this polynomial. For each eigenvalue lambda, we have the corresponding eigenspace denoted V of F comma lambda, which consists of all eigenvectors in V with the eigenvalue lambda. We call our linear operator F diagonalizable if V has a basis bold V in which the matrix of our operator F is diagonal. Equivalently, a linear operator F is diagonalizable if and only if our vector space V has a basis which consists of eigenvectors for F. We have defined the algebraic multiplicity MA of lambda for each eigenvalue lambda, or more generally for each real number lambda. So this is a multiplicity of lambda as a root of the characteristic polynomial for F. And we have defined the geometric multiplicity mg of lambda as the dimension of the eigenspace V F comma lambda. So we proved that the geometric multiplicity of each lambda is less than or equal to the algebraic multiplicity of this lambda. And our main theorem on the previous lecture was as follows, that a linear operator F is diagonalizable if and only if the sum of geometric multiplicities of all eigenvalues is equal to the sum of algebraic multiplicities of all eigenvalues, and this is equal to the dimension of the vector space. Now let us do a couple of examples for diagonalizability of linear operators. The first example, let F from R4 to R4 be the linear map which has the following matrix in the standard basis. So the matrix of F in the standard basis is the following 4 times 4 matrix: 1 1 0 0, 1 1 0 0, 2 1 1 1, 1 2 1 1. Determine whether the linear operator F is diagonalizable, and if it is, determine the diagonal form and the transformation matrix to the corresponding eigenbasis. Solution. Problems about diagonalizability always start with determining the eigenvalues. For this, we need to determine the characteristic polynomial of our linear operator. So we take the matrix of our linear operator in the standard basis, subtract x on the diagonal, and compute the determinant of this matrix. We see that this is a lower block triangular matrix with 2 times 2 blocks on the diagonal, so its determinant is equal to the product of the determinants of these 2 times 2 blocks, which coincide, by the way. So the determinant is equal to the square of the determinant of the 2 times 2 matrix 1 minus x1, 1, 1 minus x. So the determinant of this 2 times 2 matrix is equal to 1 minus x squared minus 1, and then we should square it because we have the square of the determinant. Here inside we have the difference between two squares, so we get 1 minus x minus 1 squared, this is this square, times 1 minus x plus 1 squared. And altogether we get x squared times 2 minus x squared. So we have two eigenvalues. The eigenvalue lambda 1 is equal to 0 with algebraic multiplicity 2, and the eigenvalue lambda 2 is equal to 3 with algebraic multiplicity 2. Let us now try to determine the eigenvectors for the eigenvalue lambda 1 equal to 0. These are the solutions to the homogeneous system of linear equations with the matrix when we take the matrix of our linear operator and subtract the eigenvalue on the main diagonal. The eigenvalue is 0, so we don't have to do anything. So we take the matrix of our linear operator. We see that the first and the second row are the same, so we can just forget the first row. And now we use this one to kill everything else in the first column. So we subtract twice the second row from the third row, and we subtract the second row from the fourth row. So the second row becomes the first row because we deleted the first row. So the second row in the new matrix is 2 minus 2 is 0, 1 minus 2 is minus 1, 1 minus 0 is 1, 1 minus 0 is 1. And the third row in the new matrix is 1 minus 1 is 0, 2 minus 1 is 1, 1 minus 0 is 1, 1 minus 0 is 1. So now we have here minus 1 in the position to 2. We can add this to the third row to kill this 1. So the first and the second row remain the same, and the third row becomes 0 plus 0 is 0, minus 1 plus 1 is 0, 1 plus 1 is 2, 1 plus 1 is 2. And now we have the matrix with 3 rows, and we have leading elements in columns 1, 2, and 3. So the rank of this matrix is 3. And since we have 4 columns, it means that our system has 4 minus 3, which is 1 linearly independent solution. Therefore, the geometric multiplicity of the eigenvalue 0 is 1, which is strictly smaller than the algebraic multiplicity 2 of this eigenvalue. And this means that f is not diagonalizable. So this linear operator f is not diagonalizable. And this completes this example. Example 2. Let G from R4 to R4 be the linear map which has the following matrix in the standard basis. So the matrix of G in the standard basis is the matrix minus 1, 1, 0, 0, 1, minus 1, 0, 0, 1, 2, 1, minus 1, minus 1, minus 2, minus 1, 1. Determine whether G is diagonalizable, and, if it is, determine the diagonal form and the transformation matrix to the corresponding eigenbasis. As usual, we start by computing the characteristic polynomial of G. So chi G of f is equal to, so we take the matrix of G in the standard basis, subtract x on the main diagonal, and compute the determinant. Again, we see that this is a lower block triangular matrix, so this determinant is a product of the determinants of the two 2 times 2 diagonal blocks. So we have the determinant of the 2 times 2 matrix minus 1 minus x, 1, 1 minus 1 minus x, and the determinant of the 2 times 2 matrix 1 minus x, minus 1, minus 1, 1 minus x. So the first determinant is minus 1 minus x squared minus 1 squared, and the second determinant is 1 minus x squared minus 1 squared. So we have two differences of two squares. So the first factor is minus 1 minus x minus 1 times minus 1 minus x plus 1. And the second factor is 1 minus x minus 1 times 1 minus x plus 1. So if we put all this together, we get x squared from here, and then 2 minus x from here, and minus 2 minus x from here. So we now have 3 eigenvalues. The eigenvalue lambda 1, which is equal to 0, with algebraic multiplicity 2. The eigenvalue lambda 2, which is equal to 2, with algebraic multiplicity 1. And the eigenvalue lambda 3, which is equal to minus 2, with algebraic multiplicity 1. Note that the sum of algebraic multiplicities of our eigenvalues, which is 2 plus 1 plus 1, it's equal to 4, which is a dimension of R4. So the first condition in our diagonalizability theorem is satisfied. Also, we know that if the algebraic multiplicity of some eigenvalue is 1, then the geometric multiplicity is automatically 1. So for the eigenvalues 2 and minus 2, their algebraic multiplicities coincide with their geometric multiplicities, and we don't have to check here anything for diagonalizability. So the only problem is the eigenvalue 0 with algebraic multiplicity 2. So to determine diagonalizability, we need to find the geometric multiplicity of 0. It can be 1 or 2. If it is 1, the matrix is not diagonalizable. If it is 2, the matrix is diagonalizable. So let's find the geometric multiplicity of the eigenvalue 0. So the eigenvectors for the eigenvalue 0 are the solutions to the homogeneous system of linear equations with the following matrix. We take the matrix of our linear operator in the standard basis, and we subtract 0, our eigenvalue, on the main diagonal, which means we do nothing in this particular case. So now we have to solve the homogeneous system of linear equation with this matrix. We see that the first two rows are linearly dependent, so we can remove the first row. And we also see that the rows 3 and 4 are linearly dependent, they are minuses of each other. So we can remove the fourth row. And now we have a system with only two rows, 1 minus 1, 0, 0, 1, 2, 1, minus 1. So we can kill this 0, so we subtract row 1 from row 2. We get 1 minus 1, 0, 0, it's the first row, and then 1 minus 1, 0, 2 minus minus 1, 3, 1 minus 0, 1, minus 1 minus 0 is minus 1. This is the second row. Now we have here the identity matrix formed by the first and the third columns. So we can take x2 and x4 as the free variables. Then from the first row we have x1 is equal to x2. Then x2 is equal to x2, the trivial equation for the free variable. From the second row we have that x3 is equal to minus 3x2 plus x4. And then we have x4 is equal to x4, the trivial equation for the free variable. In the vector form, x1, x2, x3, x4 is equal to x2 times the coefficient vector 1, 1, minus 3, 0, plus x4 times the coefficient vector 0, 0, 1, 1. Therefore, these coefficients vectors v1, which is 1, 1, minus 3, 0, and v2, which is 0, 0, 1, 1, these two vectors form a basis in vg, 0, in the eigenspace for g with the eigenvalue 0. In particular, we have two linearly independent eigenvectors for this eigenvalue, so the geometric multiplicity of 0 is 2. This coincides with the algebraic multiplicity, and hence the linear map G is diagonalizable. Now, to determine the transformation matrix to the eigenbasis, we need to find eigenvectors for the remaining two eigenvalues. The eigenvectors for the eigenvalue lambda 2 is equal to 2 are the solutions to the homogeneous system of linear equations, where we take the matrix of our linear operator and subtract 2 on the main diagonal. We get the matrix minus 3, 1, 0, 0, 1, minus 3, 0, 0, 1, 2, minus 1, minus 1, minus 1, minus 2, minus 1, minus 1. So let us first swap the first two rows, so we get 1 in position 1, 1. And now we can use this 1 to kill everything else in the first column. So we multiply the first row with 3 and add to row 2. We subtract the first row from the third row, and we add the first row to the fourth row. The first row remains the same, 1 minus 3, 0, 0. The second row becomes minus 3 plus 3 is 0. 1 minus 9 is minus 8, and then 0 and 0. And the third row becomes 1 minus 1 is 0. 2 minus minus 3 is 5. Minus 1 minus 0 is minus 1. Minus 1 minus 0 is minus 1. And the last row is 1 plus minus 1 is 0, minus 3 plus minus 2 is minus 5, 0 plus minus 1 is minus 1, 0 plus minus 1 is minus 1. Now we have this minus 8 here and nothing else in the second row, so we divide the second row by minus 8. The first, third, and fourth rows remain the same, and the second row becomes 0, 1, 0, 0. Now we can use this 1 here to just remove all other elements in the second column, because in the second row everything else is 0, it will not affect the rest of the matrix. So the second row remains 0, 1, 0, 0. The first row becomes 1, 0, 0, 0. The third row is 0, 0, minus 1, minus 1. And the fourth row is 0, 0, minus 1, minus 1. So the third and the fourth rows are the same. So we can remove row 4. And we multiply row 3 with minus 1 to get the matrix 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 1. This is our row echelon form. So our leading elements are in the columns 1, 2, and 3. So we take x4 as a free variable. From the first equation, we have x1 is equal to 0. From the second equation, we have x2 is equal to 0. From the third equation, we have x3 is equal to minus x4. And we add the trivial equation x4 is equal to x4 for our free variable. So in the vector form, we have x1, x2, x3, x4 is equal to x4 times 0, 0, minus 1, 1, the coefficient vector. So this coefficient vector, which we denote by v3, 0, 1, minus 1, 1, it forms a basis in the eigenspace for G corresponding to the eigenvalue 2. Finally, let us find the eigenvectors for the eigenvalue minus 2, the eigenvalue lambda 3, which is equal to minus 2. These are the solutions to the homogeneous system of linear equations. We take the matrix of our linear operator and we subtract minus 2, so we add 2 on the main diagonal. We get the matrix 1, 1, 0, 0, 1, 1, 0, 0, 1, 2, 3, minus 1, minus 1, minus 2, minus 1, 3. So the first two rows are the same, so we delete row 1, and then we use this 1 to kill this 1 and this minus 1. So we subtract row 2 from row 3, and we add row 2 to row 4. So now row 2 becomes row 1. The row 2 in the new matrix is 1 minus 1, 0, 2 minus 1, 1, 3 minus 0, 3, minus 1 minus 0, minus 1. And the third row in the new matrix is 1 plus minus 1, 0, 1 plus minus 2, minus 1, 0 plus minus 1, minus 1, 0 plus 3, 3. So now here we have 1 in position to 2. So we subtract row 2 from row 1 to kill this one, and we add row 2 to row 3 to kill this one. So row 2 remains 0, 1, 3, minus 1, while row 1 becomes 1, 0, minus 3, 1. So 1, 0, minus 3, 1. And row 3 becomes 0, 0, 2, 2. And row 3 becomes 0, 0, 2, 2. So now here we can divide row 3 by 2 to get it 0, 0, 1, 1. And then we use this 1 in positions 3, 3 to kill 3 and minus 3 above it. So we add 3 times row 3 to row 1, and we get 1, 0, 0, 4. And we subtract 3 times row 3 from row 2 to get 0, 1, 0, minus 4. And row 3 remains the same. This is now row echelon form with leading elements in columns 1, 2, and 3. So we take x4 as a free variable. From the first row, x1 is equal to minus 4x4. From the second row, x2 is equal to 4x4. From the third row, x3 is equal to minus x4. And we have the trivial equation x4 is equal to x4 for the free variable. In the vector form, x1, x2, x3, x4 is equal to x4 times the coefficient vector minus 4, 4, minus 1, 1. So this vector, which we denote by v4, the vector minus 4, 4, minus 1, 1, it forms a basis in the eigenspace for G, which corresponds to the eigenvalue minus 2. And now we can write down the answer. The diagonal form is a diagonal matrix, which consists of our eigenvalues written with the corresponding geometric multiplicities. So we have the diagonal matrix with 0, 0, 2, and minus 2 on the main diagonal. So this is the diagonal form of our linear operator G, and the transformation matrix to our eigenbases v1, v2, v3, v4 consists of the coordinates of these four vectors in the standard basis. So the vector v1 was 1, 1, minus 3, 0. This is the first column. The vector v2 was 0, 0, 1, 1. This is the second column. The vector v3 was 0, 0, minus 1, 1, the third column. And here is the vector v4, which is minus 4, 4, minus 1, 1. This is the fourth column of our transformation matrix. And this completes our second example. Now let us talk about diagonalization in Euclidean spaces. Let E be an Euclidean space with an inner product denoted by the usual bracket. Let F be a linear operator on V. Since Euclidean space has extra structure, the inner product, and in particular we not only have usual bases, we have orthonormal bases in an Euclidean space, a natural question to ask is when a linear operator F on E is diagonalizable in some orthonormal basis. In order to answer this question, let us recall that a square matrix is called symmetric if it coincides with the transpose of this matrix. And note that a special case of the symmetric matrix is a diagonal matrix. Any diagonal matrix is symmetric for the obvious reasons. Also recall that a transformation matrix between two orthonormal bases is orthogonal, meaning that the inverse of such transformation matrix coincides with the transpose of this matrix. From here, we can derive the following corollary. If F is diagonalizable in some orthonormal basis, then the matrix of F is symmetric in any orthonormal basis, let's call it E. Proof. Assume that the matrix of F in some orthonormal basis V is diagonal. In particular, it is symmetric. And let T be the transformation matrix from V to our arbitrary orthonormal basis E. Then the transpose of F's matrix in the basis E can be computed using the base change formula. So the matrix of F in E is equal to T inverse, the matrix of F in V times T. This is just the base change formula for the matrix of the linear operator. Our transformation matrix T is a transformation matrix between two O and B's, so it is orthogonal. So we can rewrite this formula as T transpose times F's matrix in V times T. And then we need to transpose this product. When we transpose the product of three matrices, we should just take the product of their transposes in the opposite order. So we get the transpose of T times the transpose of the matrix of F in the basis V, but the matrix of F in the basis V was diagonal, so it will just be the matrix of F in the basis V, and then times T. And this coincides with the matrix of F in the basis E by the base change formula and orthogonality of T. So the transpose of the matrix of F in E is equal to the matrix of F in E. So the matrix of F in E is symmetric. So if we have an operator which is diagonalizable in some orthonormal basis, then its matrix is symmetric in any orthonormal basis. So this brings us to the following definition. A linear operator F on an Euclidean space E is called symmetric, provided that there is an orthonormal basis E in this vector space, such that the matrix of F in this basis is symmetric. For example, from the previous slide, any linear operator which is diagonalizable in some orthonormal basis is symmetric. And actually, from the previous proof, we can draw the following conclusion. If we have a symmetric linear operator, so if we have a linear operator for which there is an ONB in which the matrix of this linear operator is symmetric, then the matrix of this linear operator is symmetric in any ONB. Proof. Assume that the matrix of F is symmetric for some ONB V, and let T be the transformation matrix from V to E. We do the same computation as on the previous slide. The transpose of the matrix of F in the basis E is computed by the base change formula. So this is a transpose of T inverse times the matrix of F in V times T. T inverse is equal to T transpose because T is a transformation matrix between two ONBs. So it's a transpose of T transpose times the matrix of F in V times T. This is a product of transposes in the opposite order, so it's T transpose times the transpose of the matrix of F in V, but this is symmetric, so we can just forget the transpose, times T, and again this is equal to the matrix of F in E. So this shows that the matrix of F in any ONB E is symmetric if the linear operator F is symmetric. This also gives another nice property of symmetric operators. If F is a symmetric operator, then for any pair of vectors x and y in our Euclidean space, the scalar product between f of x and y is equal to the scalar product between x and f of y. Proof. Let us choose some ONB E in our Euclidean space. Then we know that f is a symmetric operator, and we have just seen that the matrix of our operator f in this ONB E will be symmetric. So now we can compute the scalar product between f of x and y. We use the coordinates of these two vectors in an ONB. So if we have coordinates of vectors in an ONB, then the scalar product is just the sum of the products of the corresponding coordinates. In other words, it's the coordinates of f of x in this basis transposed times the coordinates of y in this basis. The coordinates of f of x can be computed as the matrix of f in our basis times the coordinates of x in our basis. Since we need to transpose, we have to reverse the product. We get the coordinates of x transposed times the matrix of f transposed, but it is symmetric, so we forget the transpose, times the coordinates of y. So this is the expression. And let us now compare it with the expression for the scalar product between x and f of y. So this is the transpose of the coordinates of x times the coordinates of f of y. And the coordinates of f of y are exactly the matrix of f times the coordinates of y. And we get exactly the same expression. So these two expressions coincide, which proves our proposition. So now we can formulate the main theorem for this lecture. For a linear operator f on an Euclidean space E, the following conditions are equivalent. Condition A, f is symmetric. Condition B, the matrix of f is symmetric in any orthonormal basis. Condition C, the scalar product of f of x and y is equal to the scalar product of x and f of y for any vectors x and y in E. And condition D, f is diagonalizable in some orthonormal basis. So on the previous slides, we have already established that A and B are equivalent. We proved that D implies A, and we also proved that B implies C. So in order to prove the theorem, it remains to prove that condition C implies condition D. So we will prove this implication. Consider the characteristic polynomial of our linear operator and let n be the dimension of our Euclidean vector space. In order to prove the theorem, we employ the trick of extending scalars from real to complex numbers. So let's consider our vector space, our scalar product, and our linear operator over complex numbers. So we consider the Hermitian space a complexification of E with the inner product, which is a complexification of our inner product. The only difference in the complex case compared with the real case is that the inner product is not directly symmetric, it is only symmetric up to complex conjugation. So this inner product between x and y in the complex space is equal to the inner product between y and x and then complex conjugate for all x and y in the complexification. If we choose an O and B in our space E, then the same set of vectors is also an O and B in the complexification. And then let f upper C be the linear operator on the complexification, which has in our O and B E exactly the same matrix as the linear operator f on E. Then we can compute the characteristic polynomial of our operator f, and since the metric is the same as for f upper C, it will be the characteristic polynomial for f upper C. This will be a polynomial of degree n, and over complex numbers, a polynomial of degree n can be written as a product of linear factors. So there are complex numbers lambda 1, lambda 2, and so on, lambda n, such that the characteristic polynomial of f is lambda 1 minus x times lambda 2 minus x times and so on. So here we use the fundamental theorem of algebra. Any non-constant polynomial with complex coefficients can be written as product of linear factors. The next observation is that all these complex numbers lambda i's, all roots of this characteristic polynomial, are in fact real. Proof. So take such root lambda I, it's an eigenvalue, and take a non-zero eigenvector v for this lambda I. Let us compute the inner product between f of v and v in the complex sense. Well, v is an eigenvector, so this is lambda I times v, inner product with v. From the left variable of the inner product, we can take lambda I out, just like it is, so it is equal to lambda I times the inner product between v and v. Next, let us compute the inner product between v and f of v. Again, this is the inner product between v and lambda I times v. But now it's in the second place, and from the second place we can take scalars only up to complex conjugate. So this is equal to lambda I complex conjugate times vv. So now let us use that our linear operator is symmetric by assumption. The matrix of f in our O and B is a symmetric matrix. So these two different computations should give the same result. So lambda I times the inner product between v and v should be equal to lambda I complex conjugate times the inner product between v and v. V was non-zero, so the length of this vector is non-zero. So if we divide by it, we get lambda I is equal to lambda I complex conjugate. And this shows that lambda I is a real number. So now let us prove diagonalizability of f in some orthonormal basis using induction on the dimension of E. The basis of the induction is easy. If the dimension of E is equal to 1, then the matrix of f is diagonal in any basis. For induction step, we have a real eigenvalue lambda 1. So the whole point of the previous lemma is to prove that f has an eigenvalue. So we take this eigenvalue lambda 1 and it has a non-zero eigenvector. Let's call it v. Let us consider the orthogonal complement to the linear span of V. The claim is that this subspace is F invariant. To check that it is F invariant, take any element W from this orthogonal complement. We want to prove that F of W belongs to the orthogonal complement. In order to prove that, we need to check that the scalar product between F of W and V is 0. So let's compute the scalar product between F of W and V. This is equal to the scalar product between W and F of V. But F of V is lambda 1 times V. V was an eigenvector with eigenvalue lambda 1. So we have the scalar product between W and lambda 1V. We can take lambda 1 out to get lambda 1 times the scalar product between W and V. And this is 0 because W is in the orthogonal complement to CV. So this is lambda 1 times 0, which is 0. And this proves that the orthogonal complement to CV is invariant under F. Now note that this orthogonal complement, this is a subspace of our Euclidean space, and it has exactly dimension of the Euclidean space minus 1, because CV is a subspace of dimension 1. And of course, our property that f of x scalar product with y is equal to x scalar product with f of y obviously restricts to any subspace. So by induction, the orthogonal complement of CV has an orthonormal basis, let's call it W, in which the matrix for the restriction of F to this orthogonal complement is diagonal. So here we use the induction assumption because we are talking now of Euclidean space of strictly smaller dimension. In particular, all vectors in this O and B in the subspace are eigenvectors for F. So now we can add the normalized eigenvector, which is V divided by the length of V, to this orthonormal basis. It belongs to the orthogonal complement, to CV orthogonal complement. So if we add it to our O and B W, we get an O and B in E, which we call E, and all vectors in this O and B are by constructions eigenvectors for F. Therefore, the matrix of F in this O and B is diagonal. And this completes the proof of the theorem. Let us now do one example of how to diagonalize symmetric operators in an O and B. Problem. Diagonalize in some O and B the linear operator F from E3 to S3, whose matrix in the standard basis is 2, 1, 1, 1, 2, 1, 1, 1, 2. So in other words, we need to determine the diagonal form for this matrix and the transformation matrix to the corresponding O and B, which consists of the eigenvectors. So we already know that a symmetric matrix is diagonalizable by the theorem, so we need to determine the diagonal form and the O and B which diagonalizes this matrix. Solution. Let us start, as usual, by computing the characteristic polynomial. So we take the matrix of our linear operator, subtract x on the main diagonal, and we compute the determinant of this matrix. We can observe that the sum of elements in each column is the same. So 2 plus 1 plus 1 is 4, 1 plus 2 plus 1 is 4, 1 plus 1 plus 2 is 4. In this case, a good idea is always to add all rows to the first row. So rows 2 and 3 remain the same, but the first row then reads 4 minus x, 4 minus x, 4 minus x. This doesn't change the determinant, but now we have a common factor 4 minus x in the first row, which we can take out. So we get 4 minus x times the determinant of the matrix 1, 1, 1, 1, 2 minus x, 1, 1, 1, 2 minus x. Now we can take our first row and subtract it from rows 2 and 4. Again, this doesn't change the determinant. We have the factor 4 minus x. The first row is 1, 1, 1. The second row becomes 0, 1 minus x, 0. And the third row is 0, 0, 1 minus x. Now this is an upper triangular matrix, so the determinant is just the product of the diagonal elements. So the answer is that the characteristic polynomial of f is equal to 4 minus x times 1 minus x squared. So we have two eigenvalues. The eigenvalue lambda 1, which is equal to 4 with algebraic multiplicity 1, and the eigenvalue lambda 2, which is equal to 1 with algebraic multiplicity 2. Let us determine the eigenvectors. The eigenvectors for lambda 1, which is equal to 4, are the solutions to the homogeneous system of linear equations with the matrix. We take the matrix of linear operator and we subtract 4 on the main diagonal. So we get minus 2, 1, 1, 1 minus 2, 1, 1, 1 minus 2. We first swap rows 1 and 3 in order to get 1 in position 1, 1. And now we use this 1 to kill everything else in the first column. So we subtract row 1 from row 2, and we add twice row 1 to row 3. Row 1 remains the same. Row 2 becomes 1 minus 1, 0, minus 2 minus 1, minus 3, 1 minus minus 2 is 3. And row 3 becomes 2 plus minus 2, 0, 2 plus 1, 3, minus 4 plus 1, minus 3. Now we have this matrix. We see that rows 2 and 3 are linearly dependent, so we can delete row 3, and we divide row 2 by minus 3. So we get the matrix 1, 1, minus 2, 0, 1, minus 1. Now we use this one to kill this one, so we subtract row 2 from row 1. Row 2 is the same, row 1 becomes 1, 0, minus 1. This is our row echelon form. The leading elements are in the columns 1 and 2, so we take x3 as a free variable, and the first row gives us x1 is equal to x3, the second row gives us x2 is equal to x3, and for the free variable we have the trivial equation x3 is equal to x3. In the vector form, x1, x2, x3 is equal to x3 times 1, 1, 1. Therefore, the vector v1, which is 1, 1, 1, forms a basis in the space of all eigenvectors for f with eigenvalue 4. So since we need an O and B, we immediately apply Gram-Schmidt method. So we simply norm the vector v1, which is v divided by its length. So we define w1 as v1 divided by its length. So v1 was 1, 1, 1. So the length is square root of 1 plus 1 plus 1, square root of 3. So w1 is 1 divided by the square root of 3, 1, 1, 1. So this is an orthonormal basis in the space of all eigenvectors with eigenvalue 4. The second eigenvalue is 1. So let us determine all eigenvectors for eigenvalue 1. These are the solutions to the homogeneous system of linear equations with matrix. We take the matrix of our linear operator and subtract 1 on the main diagonal. We get the matrix 1, 1, 1, 1, 1, 1, 1, 1, 1. So we can throw away all rows except row 1. So we have the row echelon form 1, 1, 1. The leading element is in column 1, so we take x2, x3 as free variables. From our unique row, we get x1 is equal to minus x2 minus x3. We have x2 is equal to x2 because x2 is free, and x3 is equal to x3 because x3 is free. So in the vector form, x1, x2, x3 is equal to x2 times minus 1, 1, 0 plus x3 times minus 1, 0, 1. Great, this means that the vectors v2, which is minus 1, 1, 0, and v3, which is minus 1, 0, 1, form a basis in the eigenspace for the eigenvalue 1. And now we have to apply Gram-Schmidt. So we take the vector v2 and divide it by its length. We denote the outcome by w2. So v2 was minus 1, 1, 0. Its length is root of 2. So w2 is 1 divided by the root of 2, minus 1, 1, 0. Next, we need to find the auxiliary vector w3 tilde, which is defined as v3 minus w2 with the coefficient, the scalar product between v3 and w2. Since w2 is v2 divided by the length of v2, we can rewrite it as v3 minus v2 with the coefficient, the scalar product between v3 and v2, divided by the scalar product between v2 and v2. So here is a computation. W3 tilde is -101, this is V3, minus -110, this is V2, and then the numerator, the scalar product between them is 1, and the denominator we computed here, it's 2. When we subtract these vectors, we will have 1 divided by 2 times -1 -1, 2. So let's forget the rational coefficient here, denote by W3 2 tildes the vector -1 -1, 2. And now we simply norm it. So W3 is W3 2 tildes divided by its length. So the length here is 1 plus 1 plus 4 is root of 6. 1 divided by root of 6 -1 -1, 2. So recall that the vector W1, which is 1 divided by root of 3, 1, 1, 1, was an ONB in the eigenspace for the eigenvalue 4. And the vectors W2, which is 1 divided by root of 2, -1, 1, 0, and W3, which is 1 divided by root of 6, -1, -1, 2. These two vectors was an ONB in the eigenspace for the eigenvalue 1. For symmetric operators, eigenvectors with different eigenvalues are arithmetically orthogonal, so we can simply put all these vectors together to form an ONB in E. So the transformation matrix to this ONB will be just the vector W1 as a column, the first column, the vector W2 as a second column, the vector W3 as a third column, and then, since these are three eigenvectors, the corresponding diagonal form will be the diagonal matrix with the eigenvalues 4, 1, 1. So 4 is the eigenvalue of W1, 1 is the eigenvalue of W2, and 1 is the eigenvalue of W3. And this completes our example. Let us finish with some additional problems and questions. Question 1. Let G from Rx3 to Rx3 be the linear operator which sends f of x to x plus 1 times f prime of x. Determine whether f is diagonalizable, and if this is the case, determine the diagonal form and the transformation matrix to the corresponding basis. Question 2. Let G from Rx3 to Rx3 be the linear operator which sends f of x to f of x plus 1. Determine whether f is diagonalizable, and, if this is the case, determine the diagonal form and the transformation matrix to the corresponding basis. Question 4. Let f be a symmetric linear operator on some Euclidean space E, and V be a subspace of E which is f invariant. Prove that the orthogonal complement to V is also f invariant. Question 4. Prove that, for a symmetric linear operator f, the eigenvectors with different eigenvalues for f are orthogonal. Question 5. Diagonalize, in some orthonormal basis, the linear operator f from E3 to S3, which has the following matrix in the standard basis. So the matrix is 1, 0, 1, 0, 1, 0, 1, 0, 1. Thank you very much, and see you next time.